Welcome to Study Loop.
So once again, we're given a new problem. And then this time it happens to be a sphere. So this is a sphere, and the mass of the sphere is given us 20 kilograms. And there's a dart that's fired that way with the mass. It's still dart, and with the mass of um, 5 kilograms, or 5.00 kilograms. We don't know what the initial velocity is, so that's what we want to find out. Uh, we're also given that the sphere is hanging from a hook, so it's going to swing and go around in a circular path like that. And there's going to be at the top, you have the dart and the sphere sticking together. This radius of the string from the hook is given us 2.8 meters. That's the radius. And so we're interested in finding the initial velocity. The first thing we have to do is remember that the law of conservation of, not the law, but Newton's second law. Newton's second law says that the sum of the forces in a system equals to the mass and the acceleration. At the top right here, there's a centripetal force, Fc, that's responsible for for balancing out the weight. So the ball is trying to move that way, but the centripetal force is pulling it that way. And so Fc equals to mg. M, this is the final velocity of the sphere and the dart. We have to change that a little bit. So when they combine together, this is before they combine, and then this is after they combine. So after they combine, they have the mass of the sphere and the mass of the dart together. So in terms of centripetal force, remember, typically your centripetal force is mv squared over r. But on this one, when they combine, you get mass of sphere plus mass of dart, and then the velocity, the initial velocity. So when they combine, they're going to have an initial velocity that takes them all the way up. You're going to have a velocity that's the velocity of the sphere and the dart, and the final velocity right here. So we don't know what that final velocity is, but it's responsible for the centripetal force at that point, squared over the radius, and that's equivalent to the combined masses times acceleration due to gravity. These two are going to cancel out. So we have the combined sphere and dart velocity, the final, is the same as the square root of rg. Okay, so that's one part of the problem. And now we're going to use the law of conservation of energy to determine the velocity, the combined velocity at the lowest point. So when they stick together, this system is like this. So initially they stick together, and so we don't know what that combined velocity of the sphere and the dart is when they stick together, but we do know what this combined velocity is right here. So this combined velocity, if you go back, we just found it. It's the final. So of the sphere and the dot. So this should be D. And that happens to be radical 2 radical RG. So using the law of conservation of energy, we see that the initial energy of the system, equals to the final energy of the system. And now we're only focusing on what happens when you combine the sphere and the dart, like that. So the initial energy of the system is the kinetic energy of S and D. Initial, that becomes the kinetic energy of S and D final, plus the potential energy, which is MS, that's MD, G, H. This height right here, so this one, so this is going around like that, and this height, this distance height, H, equals to twice the radius. Because if you go back, you see that the radius is 2.8, but then if you build all the way up until the top, it becomes twice the radius. We don't have the initial, this is MS, the initial potential energy at the base equals to 0, because this height right here is 0. And so we don't include it right there. We ignore that. Plugging in the variables, we have 1/2 m mass of the sphere plus mass of the dart, and then the initial velocity of the sphere and the initial velocity of the dart, we want to square that, equals to 1/2 mass of sphere and mass of dart times final velocity of the sphere and the dart, final velocity, plus what we have right here as the potential energy for the combined system when the when the dart embeds itself on the sphere. And this is 2r. That height, this height right here, as you can see, is twice the radius. This is going to simplify our problem because those masses will cancel out. And so we're left with, we can multiply everything by 2. These cancel, that cancels. So the initial velocity of the sphere and the dart right here squared is given by the final velocity of the sphere and the dart. This is squared plus 4gr. Okay, that's what we're given. And so in the next page, we want to solve for the value, the initial value, this one right here. So the initial value of the sphere and the dart is going to be the square root of the final value squared plus 4gr. But if you can recall, the final value, this one is radical rg. So this equals to, we have another radical rg, and then that squared plus 4gr. And so this becomes, the square cancels the radical. We have rg plus 4gr. And so this is going to be 5gr. That's the initial combined velocity when the dart embeds itself inside of the sphere. In the next page, we'll use the law of conservation of momentum which says that the initial momentum of the system equals to the final momentum. So the initial momentum of the system equals to the final momentum. Initially, before anything happens, we have the mass of the sphere, or rather the mass of the dart, and the initial velocity plus the mass of the sphere and the initial velocity of the sphere. If you go back, you see that the initial velocity before anything happens is 0. The initial velocity is 0. This is 0 meters per second. And then if we come back here, so this is going to be 0, equals to the final, after collision. After collision, they combine and move together. So that's the mass of the sphere, mass of D, and then the final velocity, when the initial velocity when they collide, and that happens to be a sphere and D. This is before collision, and this is after collision. Our target is this value right here. So initial velocity of the dart before they combine is mass of that one, and then velocity of D, and the combined initial velocity. So that's the combined right here. When they collide, the moment they collide, it acquires a certain velocity. We don't have to think about, so we have it right here. Okay, this one right here. We already know what the final is, and the final helped us get the initial. So when they combine, if we go back, now we can plug in the numbers. We say this one is mass of sphere is 20 kilograms plus mass of dart is 5 kilograms times that velocity that we just got, which is this one, radical 5gr. That's the combined initial velocity of the mass, the sphere, and the dart, and then all of the mass of D, which is 5 kilograms. Okay, which is 5 kilograms. So we'll complete the problem in the last page just by plugging in the numbers. So we get VDI equals to 25 kilograms. So we're combining them times radical 5gr. So this is 5 times 9.8 meters per second squared times the radius, which is 2.8 meters, all over 5 kilograms, like that. These two are going to cancel, so we'll be left with 5 right there. And then we can use a calculator and say this is radical. This is radical square root 5 times 9.8 times 2.8, like that, and then we have to multiply that by 5. So it's going to give us an initial value that we wanted of 58.57 meters per second. That's the solution to the problem. Just as a recap of what happened, we had a steel dart fired and it had a mass of 5 kilograms. We want to find its initial velocity. That's going to make sure that this thing barely goes round in a circle like that. And so when they collide, when the system collides, we use Newton's second law to see that the centripetal force equals to the weight of the combined system. We solve for the final velocity of the combined system at the top, and then we move on and use that final velocity of the combined system together with the law of conservation of energy to see that the initial energy equals to the final. The initial kinetic energy of the system, the combined system, that's the steel sphere, and the steel dart is gonna equal. Remember, we don't have an initial potential energy because the height is 0, so we only have an initial kinetic energy. Is gonna equal the final kinetic energy and the final potential energy, and so we make those two equal to get the initial velocity just when they combine with each other, and that initial velocity is the square root of this value right here. It's the square root of that value, this value right here, this whole value. Okay, it's the square root of that. Just don't forget the square, SDF final squared. This one is squared, and then 4GR. If we square the final value that we got right here, we're going to get rid of the radical, and that just means that we have RG only, combine it with 4RG, and this is always why it's good to keep the variables, because they simplify and it makes your life easier. And so using the law of conservation of momentum, the initial momentum of the system equals to the final momentum of the system, and then we find the initial velocity before the steel dart collides with the sphere. Hope you enjoyed the problem. Have a wonderful day, and if you have any questions, send them my way. Thanks, and bye-bye.